dive right into the fascinating world of physics with the free electron gas model in metals. This model is a key player in our understanding of how electrons behave in a metal's crystal lattice. Picture a metal with its closely packed atoms arranged in a regular pattern. Now imagine that some of the electrons in this structure are free to move about, not tied to any particular atom. This is the basic premise of the free electron gas model. The model likens these free electrons to an ideal gas. Just as gas molecules bounce around in a container, the free electrons move freely within the metal, colliding with each other and the metal ions. This is a simplified approach, of course. The reality of electron behavior in metals is much more complex. So, in essence, the free electron gas model simplifies the complex nature of metals by treating the electrons as free particles. Understanding any model starts with its assumptions. The free electron gas model is no different. This model is based on a few key assumptions that simplify the complex reality of electron behavior in metals. The first assumption is that the electrons in a metal are non-interacting. In other words, they move independently of each other. This means we can ignore the complex interactions that would otherwise occur between electrons. Secondly, the model assumes that the electrons move in a uniform potential. Picture a flat landscape where the electrons can move freely without any hills or valleys to navigate. Lastly, the model considers the crystal lattice of the metal as a constant potential. Essentially, the electrons are free to move within this potential, like birds flying in the sky. These assumptions, while not entirely accurate, provide a simplified way to analyze the behavior of electrons in metals. The free electron gas model, with its simplified assumptions, still manages to have significant applications. One of the most noteworthy is its ability to explain the electrical and thermal conductivity of metals. In essence, the model paints a picture of metals as a sea of electrons, freely moving and colliding, giving rise to these conductive properties. Furthermore, this model is instrumental in explaining the electronic heat capacity of metals. It's all about how these free electrons absorb and distribute thermal energy, a key aspect of how metals respond to heat. By shedding light on these behaviors, the model enables a deeper understanding of the fundamental properties of metals. So, even though the free electron gas model makes some broad assumptions, it's still a powerful tool. It provides a foundational understanding of the properties of metals, from their conductive behaviors to their heat capacities. Despite its simplicity, the free electron gas model offers valuable insights into the properties of metals. Like any model in physics, the free electron gas model has its limitations. For instance, it struggles to accurately explain the behavior of metals at extremely low temperatures. The model assumes a continuous sea of electrons, which doesn't quite hold up when the temperature drops, and electrons start behaving in unexpected ways. This is why it falls short when we try to use it to understand the fascinating phenomena of superconductivity, where resistance in a material drops to zero as temperature approaches absolute zero. The model also simplifies the complex nature of a metal lattice, treating it as a continuum rather than acknowledging its discrete crystalline structure. This limitation can lead to inaccuracies when predicting certain properties of metals. To sum up, the free electron gas model is a simplified representation of the behavior of electrons in metals. Despite its limitations, it provides a fundamental understanding of metal properties and remains a seminal concept in the study of solid-state physics.